In this video, we discuss displacement mapping and subdivision. We're going to be using a simple cube and a simple plane object for this lesson. I'm going to go to Create menu in the Material Manager, Arnold, Surface, and create a brand new utility shader and assign it to the cube for now. Also, let's run the IPR and open up the utility shader and change the shade mode to Lambert and overlay mode to Polywire. Now we can see the edges of our geometry in the render, which can help us to understand the subdivision parameters a bit better. I'm going to right click on the cube, go to C42A tags and add an Arnold parameter tag. Now go to the subdivision tab. First off, you have the subdivision type, which is non-linear and Cath-Clark. We have iteration, which specifies how many times the mesh should be subdivided. So when the type is set to none, there would be no subdivision, obviously. When set to linear, as you increase the number of iterations, you are adding more polygons to your geometry without changing or compromising the shape of the geometry. Now, when the iteration is set to 0, there would be no subdivision. When I increase it to 1, we have generated 4 faces off of each face. When I increase the iteration to 2, we have quadrupled the number of polygons again. Go to 3, we have quadrupled the number of faces again. So each time you increase the iteration by 1, you will end up with 4 times more polys compared to before. But in linear mode, you keep the original shape of the object. Let's change the subdivision type from linear to Cath-Clark, and immediately we have a sphere instead of a cube. The Cath-Clark algorithm is used to create smooth surface by recursive subdivision surface modeling. So as I increase the iteration, I'm not only adding more geometry, I also make the geometry rounder and overall smoother. Let's set the iteration to 3. For displacement maps that you get from sculpting tools like ZBrush or Mudbox, you normally need to change the subdivision type to Cath-Clark. Then we have adaptive metric, which allows us to have some level of adaptiveness in our subdivision. So for example, based on how close or far we are away from our object, we can have more or less iteration applied automatically. At the moment, it is set to auto, and as I increase my adaptive error to, let's say, 60, you can see we have smaller amount of polys. And if I get away from my cube and rerun the IPR, because we are far away from our cube and we don't possibly need as much detail as before, we're gonna have smaller iteration value and therefore less polygons. If I get closer to my cube and run the IPR again, we're gonna have more iteration and polygons again. Let me just get away from the cube and rerun the IPR. Now as I decrease the adaptive error value, we are gradually decreasing that adaptiveness, and at 0 we have no adaptiveness no matter what. Let's get back to the camera again. Also, we have 2 adaptive modes beside auto: edge length and flatness. When set to flatness, the curvature of the mesh in pixels is the feature used to choose the adaptive subdivision level. When using edge length, the length of the polygonal edges in pixel is used. And when set to auto, flatness will be used when no displacement map is applied, and edge length will be used when a displacement map is applied to the mesh as well. Then there is adaptive space with raster and object modes. Raster corresponds to adaptive subdivision in raster space, and object corresponds to adaptive subdivision in object space. Now, when instancing, you should use the object mode, and when you have only one object, the raster mode will work. You probably don't need to change this option unless you have some instancing going on in the scene. Also, you can read about these options in the Arnold Sport website. We have UV smoothing, which controls the algorithm used to smooth the UV vertices in the mesh when you are subdividing it. So pin corners pins the 4 corners of our UVs, and the rest of our UV might move as we subdivide our mesh. Pin border will pin all the edges of our UV. Linear will pin everything, so the UV will stay as it was before subdividing, and smooth will basically move the UV vertices as we subdivide our mesh. No pinning basically in this mode. Also, if you noticed any faceting happened in your specular highlights, when you have anisotropy, you can enable smooth tangents to get rid of the faceted look by enabling smooth tangents. There is this ignore frustum culling. If you go to the render settings main tab and under the subdivision, we have this frustum culling feature that we can enable it, and in this case only the polygon faces that are in the camera view will be subdivided, and anything out of the camera view will not be subdivided. Let me show you how this works. I'm going to unhide this big plane and hide the cube for now, and assign the utility shader as well to the plane so we can see how the polygons are being subdivided. Now add an Arnold parameters tag and increase the iteration type to linear and 3. If I get out of the camera in the viewport, and in the IPR make sure the active camera is the default viewport camera, back to the render setting now. Let's say I want to make sure only those polygons that are visible to this camera will be subdivided so we can save some resources on our machine. Simply enable frustum culling and define that camera as the dicing camera. Now, as it is visible in the IPR, only those polygons that are in the viewing frustum of the camera are subdivided. Frustum padding allows you to add some safe padding to the frustum. So if I add like 30 centimeters of padding, some of the out of frustum faces will be subdivided as well. This max subdivisions value here allows you to define a limit to the number of subdivision iterations in your scene. Thereby, no object can have a bigger subdivision iteration than the defined value here. Back to the Arnold parameters tag, we had this ignore frustum culling, which would disable global frustum culling for this particular geometry. Now that we have this foundation about subdivision, let's discuss displacements mapping, which allows you to create real geometric details based on a texture. The difference between displacement mapping and bump mapping is that bump mapping was just an illusion, right? We wouldn't alter the geometry, but displacement mapping actually creates and alters the geometry. And it is obviously much, much more realistic. Now let me show you how displacement mapping works. I'm going to hide the plane and unhide the cube. Start by creating a new standard surface shader, and I'm going to rename it to normal displacement or something like that. Open it up and open the network editor for this shader. As you can see down here, we have the Arnold displacement port. I'm going to press Ctrl Tab and search for displacement. And we have this displacement node. Let's add it to the scene. This node contains two types of displacement mapping, normal and vector. Normal displacement map is the more traditional one when you have a grayscale image and you want to add displacement based on that grayscale texture. And vector displacement can also displace the mesh in different directions besides only up and down that we have with normal displacement mapping. When you add a displacement map node, it will automatically be set as the Arnold displacement shader. You can connect it manually as well. The next thing would be to define the grayscale image which we want to drive our displacement mapping with. So add an image node and load this brick disp map. And let's see it on the cube. It looks like to be too small, so I'm going to set the U and V scales to around 0.5.